I'm Rulon VanDyke, Keysight Technologies. I'm do RF system simulation. Today we're going to talk a little bit about 5G RF architectures and being able to do designs with less iterations, with no iterations, and using off-the-shelf components. And so, all right. So also in this presentation, we're going to look how we take a data that we can get from vendors, which is in the form of the data sheet information, which has frequency response. Usually, sometimes the data is characterized over temperature and bias, and a lot of that today is, it's not used in simulators. S parameters are popular and have been for a long time, but we have really no quick way of getting the data sheet values and bringing them into the simulator that we can actually characterize the system over frequency and temperature and voltage. And I'll show you the results of this. First, I want to basically just go right to an experiment that we did. We built a little 5G transmitter, and this is the test setup here. And here's some off-the-shelf components, and you see those in the white boxes there. So on the very left is a mini circuits IF amplifier, and then there's an X microwave block there in the middle that does an up conversion to 18 gigahertz. And then at the end we have an API Technologies amplifier. And so this was our test setup. And I want to just go basically right to the results. Okay, this is the punchline. And so we did this test over 3 different power levels, and we looked at some typical characteristics that you would look at. Oh, I may just mention that this was an LTE downlink test. So we looked at channel power, we looked at ACPR, and we looked at EVM under these 3 conditions. Now, of course, the measured results, we all know what that is. That was the test setup that we did using our equipment. Also, we did a time domain simulation. So what we do is we extract an RF model from the RF, and then we run that in the time domain, and then go ahead and look at these results, and that's what you see in the middle. Now, the estimated is something unique that we do, and it's a patent-pending technique that we developed, and it allows us to do estimation. This is completely done in the RF domain or in the frequency domain. And some of the advantages of this is it's many times faster than data flow or a time domain simulation. But the greatest capability that we have is to be able to put metrics, digital modulation metrics, like EVM, ACPR, BER, on a level diagram, and then be able to do root cause analysis. And I'll show you that here later in the presentation, where we can actually pinpoint the weak links in the system, and that's one of the values of this particular technique. And you can see the results. The EVM for the estimated is not as accurate as the measured and simulated. Well, we would expect that. But what it helps us do is pinpoint the problems. So I want to pop up at a higher level now, and let's just talk about RF system analysis in general. Generally, there's 2 aspects of this. There's the architecture phase, which is done in the beginning. And what's important there is we want to evaluate different architectures very quickly. Maybe the accuracy doesn't need to be as good, but we want to be able to quickly identify the weak links in our particular architecture and be able to optimize that. Generally, spreadsheets are used for that particular task. And then, of course, there's the verification part, which is we have the design all done, we have accurate modeling, we're okay if it takes a little bit longer to simulate because we're looking for high accuracy. And typical tools like this are, circuit envelope. All right, so I want to focus just on the front end stuff, on the architecture in the front end. And so, as I mentioned, what's common today is spreadsheets, and spreadsheets are used for this task a lot, or some people roll their own. Many companies roll their own. But there's a lot of problems with this technique, and there's a whole list of things, right? How do you do frequency dependence, temperature dependence, VSWR, multiple paths, image noise in a mixer? I mean, that's a big deal. Generally, the spreadsheets just look at cascaded noise figure equations. So one of the things that that we have come up with here, well, here's our 5G transmitter. And so this is a schematic diagram of the hardware that I showed at the beginning. And so you see a mini circuits amplifier over here at the left. There's an X microwave block there in the middle that does the up conversion. And then we have the API amplifier and then another X parameter filter at the end. And I'll talk a little bit more about this at the end, but we're taking 2.8 gigahertz at the input in the IF. The LO is about 5 gigahertz. We're tripling that, filtering it, limiting it. That's what's running into the mixer. We take the sum of that and we end up at about 18 gigahertz. All right, so how do we eliminate design iterations? Well, part of that is to leverage the data that we have available from the manufacturer. And this is the data in the spreadsheets. And so this is a typical mini circuits amplifier and a mini circuits data sheet here. And we see the typical response curves. But notice that you've got P1 dB versus frequency, IP3, right? How do we handle that? Well, we now have the capability that we can take that spreadsheet data, or it could be in a GM-diff format if you're familiar with ADS. And we have a part library. Well, let me go back here. We have a part library with mini circuits. We're working in conjunction with mini circuits, where you can just drag and drop the part on the schematic, and all this data is automatically imported. So the user doesn't have to do any translation between the data sheet and the simulator. It's all seamless. And that's what we're seeing here. So you see the data sheet the data set highlighted on the left on the workspace tree in the little red box. That's the data set that's been imported. These are 3D graphs generated from the data. So here you were looking at return loss versus frequency and temperature, gain versus frequency and temperature, P1 dB versus frequency and temperature. And what we do internally is we have a multi-dimensional interpolator. So if you want to look at this at a certain temperature or a certain voltage, we get the frequency slice for that particular operating condition, and we use that internally in the simulator, and it's all automatic. Intermods and so forth will automatically come out at the right amplitude. Now, maybe you don't have a data sheet and you just want to do something really quick. One of the things that we have done is allow you quick entry into the data. So you see on the left is generally the traditional way that you would enter the values. But now you can enter those as vectors. Now that may be a little bit cumbersome if you have a lot of points, but we have the frequency tab where there's a one-to-one correlation. So you can just type the values in the frequency tab. It will automatically transport them into vectors. If you don't have vectors for everything and you want to use fixed values, it'll go ahead and use fixed values, just to make it easy for the designer. All right, here's one of the great value adders that we have, and that's this estimation technique. And so we're seeing level diagrams here, or budget analysis diagrams for the actual transmitter that we built. And this technique allows us to do root cause analysis on the design. And so on the diagram on the left, you see ACPR as it goes through the chain. And on the right, you see EVM as a percent as it also goes through the chain. But because we can keep track of the EVM due to thermal noise, intermods, phase noise, we can show the individual contributors on the level diagram. So if you look at this level diagram, the green curve is intermods, and the purple one is phase noise. Now this simulation or this estimation was run at minus 20 dBm. And so you can immediately see, all of us in this room could immediately pick out the fact that the mixer is the weak link in the system, both due to the, for the ACPR and the EVM. And there's, you might not be able to see it, but you know, there's the mixer symbol there at the bottom of the level diagram, so you can quickly identify that. But of course, if you drop the power level, you know, the EVM due to phase noise is going to become dominant at some point, right? And this is very valuable to a designer because we know exactly where to start poking to fix the problem. All right, and so here is the time domain simulation that we ran. Once again, the RF model was extracted, okay, it was put into the time domain simulator. We're running modulation analysis through this. And so this is the real spectrum due to the LTE downlink signal, and you see the constellation here. Okay, now, so I'm a software developer, not a hardware designer, and so I needed a way to get hardware very quickly to verify this particular concept and do this particular design. So I used the next microwave block, and that's what you see in the upper left corner. This is like microwave Legos. And so they have a system where you can quickly design this, this middle piece of the transmitter, which was IF in, and there's a mixer, and then an up converter. At the top, on the right, you see the 5 gigahertz LO, and then it's multiplied and amplified, and then it comes down into the mixer, which is the little black dot there over at the left. And then we have an 18 gigahertz filter at the output. And so this system, X Microwave, helped me get part of this design done very quickly. Now, and so what you'll also see here is ACPR measurements using our spectrum analyzer software. You see it at 2 different power levels. Also, our VSA software that we have, and this is how we measured the EVM, and those are the 2 results that you see there at the bottom. This particular architecture simulator is available in ADS, in Genesis, and System View, and it allows designers to do root cause analysis, find the problems associated with your design, be able to do the architecture and the architecture changes up front before you commit to hardware. Because once you commit to hardware, it's very expensive to solve the problem. So in summary, we can now take data sheets and set a format and a standard for the industry where we can use system parameters directly into the simulator over frequency, temperature, and bias conditions. And so you can quickly do designs. You can look at the budget analysis and EVM analysis, do the root cause analysis, and pinpoint the issues on the level diagram. And please come by and see us at the booth. X Microwave also has a booth here up along this side. All right. Thank you. Is there any questions that?
Yeah, Rulon, you showed the data entry point where they had, as a function of frequency, you had gain, noise figure, IP2, IP.
You want this?
Yeah, that one. Yeah. So, how do you add on to that the temperature variation?
Okay, the temperature variation is in the model. You don't. It's not highlighted here because there's a scroll bar at the left, but on the amplifier itself, there's a temperature parameter. And so you can make that an equation or whatever, and you set that and run it. Yeah. All right, thank you.